All right, welcome everybody. Today we're going to talk about Calc Lesson number 26. This is day 4 of related rates, and it's all about rectangular prisms and troughs. So before we even get started, we kind of have to have a visual about what these shapes look like. So over at the left-hand side there, this would be your rectangular prism. You could call the one at the far right, you might hear that referred to as a triangular prism. And then the one in the middle would be a trapezoidal prism. And in case you didn't catch on, they are named based on the shape of their face. So in the first one, the face is a rectangle, whereas in the middle one, the face is a trapezoid, whereas in the last one, you have a face that is a triangle. And so the trapezoidal prism and the triangular prism, those are mostly just called troughs. So if you see that word, that's what they're describing. You probably have seen them before without even realizing it on a farm. Usually it's what pigs or horses eat out of. It's filled with food or water. So if you want to kind of have an idea of what a trough is. So for each of these, we're going to be talking about the volume. So the volume of a rectangular prism, I don't think we even wrote because the volume of a rectangular prism would just be length times width times height. Then, as far as the other two formulas go, you would give the formula based on, so that's this one here and this one here, in order to find the volume, really of all of them, but for the second two in particular, it's the area of the face times the length. So in the middle one, you'd find the area of the trapezoid times the length. And then for the third one, you'd find the area of the triangle, then times the length. So just to kind of see how that translates, the triangular prism, the volume of a triangle is 1/2 base times height times the length. For the one in the middle, the area of a trapezoid is 1/2 the height times base 1 plus base 2, and then you're going to multiply that times the length. So these two formulas, respectively. So now that we kind of have a visual about what the shapes are going to look like, and now that we've reviewed our formulas, let's go ahead and take a look at the problems. So notice here for the problems that we no longer have the boxes. You know, now that we've done several days of these, you kind of get a little bit better at knowing what you're given and knowing what you need to find. And so you don't have to really be constrained by the boxes anymore. You can play it a little bit fast and loose. You can also kind of, skip some steps depending on if you're getting better at this. I might not write my units in every step. I might just make sure it's correct at the end. So again, depending on your comfort level, you can kind of approach the problem in that manner. So here in number 1, a gas station has a rectangular tank underground. We know that the tank is 30 feet long by 20 feet wide and 10 feet tall. A worker lowers a dipstick into the tank and notices that the height is dropping 1 foot every 2 hours. How fast is the volume of gasoline changing? So the fact that this is a rectangular tank and it's holding something is how I know that it's going to be a rectangular prism, and it has to look like the shape there. I'm not as good of a drawer as Miss Vitrone, so I found my shapes online, and if you're not that good of a drawer either, then of course, no worries. So I do have some information that's given to me here. I know that the tank is 30 feet long, so I know that the length is 30 feet. I know that the width is 20 feet, and I know that the height is 10 feet. Here, because of the fact that they're ultimately asking how fast is the volume changing, we know that this has something to do with volume. The volume of a rectangular prism is, of course, length times width times height. One of the most important things you want to ask yourself for all the problems that we're doing today is anything constant? Any values that are constant don't change, and if you know what they are, you're actually able to plug them in to the original formula. So taking a look at what's happening here, you have this tank and you are filling it. If you are filling it, the height is changing. So maybe you have it filled up to here. Maybe you have it filled up to here. No matter how high you fill it, the length and the width are both constant. So length and width are both constant. The fact that the length and the width are both constant actually means you can plug them into your equation right away. So you're going to plug in for the length, 30. For the width, you're going to plug in 20, and then the height remains an h, which means that your new volume equation is equal to 600h. Well, that makes life pretty darn good because I've only got two variables. Then what else do we know here? So how fast is the volume of the gasoline changing? So what I'm ultimately looking for is I'm looking for dV dt. What else do I know? Well, I know that the height is dropping 1 foot every 2 hours. So 1 foot every 2 hours, I would actually rather convert that to just 1 hour. So if it is dropping 1 foot every 2 hours, then it is dropping half a foot every hour. Because it's dropping, that's going to be a negative 0.5 feet per hour. Believe it or not, that's everything that I need to solve. So I'm going to go ahead now and take my volume equation, and I'm going to differentiate with respect to t. So dV dt is equal to 600 is a constant. H goes down to h to the 0, which disappears, followed by dH dt, which means that dV dt is equal to 600 times negative 0.5. Which means that dV dt is equal to negative 300. And then because this is a volume and because it's in feet and hours, I know that it is cubic feet per hour. And that's going to go ahead and be my answer. So take a look. Again, notice what's different about this problem compared to other problems. So one, it's becoming more and more important that you draw the picture, or else you might not have a good idea of what's going on. Number two, notice that I don't have any boxes, so I'm kind of writing information as I locate it. I'm kind of thinking to myself, well, what's obvious? What's not obvious? So there's someone else who maybe could have done the steps in a slightly different order, but still got down to the same answer. And then, of course, notice I'm getting a little bit lazy with my units. As long as you have the correct cubic feet per hour in the answer, if you don't show it every step along the way, that's okay. So that, of course, is the easiest shape. So let's go ahead and talk about a more challenging one. So the cross section of a water trough is an inverted isosceles triangle with its top edge horizontal. So translating all of those words, you get this picture that is shown to the right. An inverted trough means it has to look like this with the point on the bottom, or else it wouldn't be able to hold anything. You have to have the top edge horizontal, or else you wouldn't actually be able to set up on a formula. And the fact that it's an isosceles triangle, that's important to know too, so that you know that two of the sides are equal, which again, that has to be true in order for you to be able to solve this easily. So the triangle has a base of 2 meters and a height of 1 meter. The trough is 5 meters long. Water is being pumped into the trough at 50 cubic centimeters per second. How fast is the water rising when it is 40 centimeters deep? So take a second to digest. Your teacher will pause, read the problem, look at the picture, and there is one big glaring thing that hasn't yet been true that we have to deal with, and that is the fact that I see meters, I see cubic centimeters, and I see centimeters. So it is not possible to have units that don't agree. So if you have units that don't agree, you have to convert to one or the other. So I'm going to suggest that you convert everything to meters. So if you're converting things to meters, please keep that in mind for when you go to list your information. So we are talking about the volume of this shape right here. So you can either get the formula from the previous slides, or remember that the volume of a prism is equal to the area of the face times the length. So because the face is a triangle, that would be 1/2 base times height, then times the length of the trough. Then remember the important question, is any value constant? So think about what happens as you fill up this trough. As you fill up this trough, let's say you filled it up to here. If you filled it up to here, you would have a certain base and you would have a certain height. Well, what if you filled it up to here? You would have a different base and you would have a different height. So the base and the height is clearly changing, but guess what's not? The length of the trough. So the length of this trough is constant. So because the length of the trough is constant, remember, you're allowed to plug that in right away. So the trough is 5 meters long. You can either draw that on your picture. So the length is equal to 5 meters. You could do it here. Whatever makes the most sense to you, because it's constant, you would say 1/2 base times height times 5. Simplify, you would get that that is equal to 5/2 B times H. Let's talk about what other information we have. So water is being pumped into the trough at a rate of 60 cubic centimeters per second. So that's the change in volume, which is dV dt. Remember, we want to convert all of our centimeters to meters. So how do I do that? You divide by 100. So 60 divided by 100. We're going to say that dV dt is equal to 0.6 cubic centimeters per second. They are asking how fast is the water rising when it's 40 centimeters deep. So how fast is the water rising? So getting higher and higher and higher. That means we are looking for dH dt. We also want to look here and see if there is any other information that we know. So take a look, volume equals 5/2 base times height. If I was to try to take that derivative, I would get dH dt, which is what I'm looking for, and I would also get dB dt, which unfortunately I do not know. I do not know the rate at which the base is changing. Just like the previous lesson with the cone, if you didn't have enough information, you have to go back, find some, find some other piece of information about the shape and use that to make a substitution. The piece of information that I have not yet used is that this triangle, has a base of 2 meters and a height of 1 meter. So I'm going to take that information and I'm going to create a proportion. The relationship of the base to the height is 2 to 1. I'm going to cross multiply, and that is going to tell me that the base is equal to 2 times the height. So that is what I need, because if I substitute that into my next slide, I am going to have just a problem all in terms of H's. So I left myself room on the next slide to go ahead and make that substitution. So when I make that substitution, I'm going to get volume equals 5/2. In for B, you're going to put a 2H times H. So your volume equation is going to be, cancel the 2's, 5H squared. Again, so beautiful, so simple. None of the work that you have done so far is calculus. It's all geometry and algebra. That's the hard part. So now you're going to be doing the easy part, which is the calculus. So when you go to take the derivative, you're going to take the derivative of the left side, which is going to give you dV dt. When you take the derivative of the right side, you're going to bring down the 2 to get a 10, then the h to the 1 less power, and then times dH dt. From here, you're going to plug in any of the values that you were given. So 0.6 for dV dt times 10 times 0.4, because that's the time in question you were trying to solve for. I didn't write that on the previous slide, but they asked you to solve it when this was exactly 40 centimeters. So again, you're going to divide that by 100, and that is going to make your H 0.4 meters. So if you plug that 0.4 in and then dH dt, 6.6 is equal to 10 times 0.4 is 4. dH dt, divide by 4. So dH dt is equal to 0.6 divided by 4. That's going to give you 0.15. And then because this is dH dt, you're in meters per second. So that is the rate at which the height is changing at exactly the time when the height is 40 centimeters or 0.4 meters. So again, similar to what we did with the cone, you had to make a substitution to get rid of the base and have everything in terms of height, or else there would be no way for you to solve. Okay, and finally here we're going to talk about number 3. So here we have a water trough that is 6 meters long, and it has a cross section, which means a face, which is the shape of an isosceles trapezoid. So here's my isosceles trapezoid here, and again, it's important to know that it's isosceles so that we know that the two sides are equal. It's 30 centimeters wide at the bottom and 80 centimeters wide at the top and 50 centimeters high. So if we wanted to add some of those values in here, so 30 centimeters at the bottom. Before I do that though, if you went ahead and read all the way through, just like the previous problem, we have centimeters, and then we also have meters. So my advice whenever you have a problem like this would always be to convert to meters. And of course, just to make it clear, there are 100 centimeters in 1 meter. We talked about that in the previous slide, but just to be sure. So the fact that they are telling you that it's 30 centimeters wide at the bottom, that's how I know that base 1 is going to be equal to 0.3 meters. Then it's 80 centimeters wide at the top. So that's how I know that base 2 is going to be equal to 0.8 meters. Then it's 50 centimeters high. So that's how I know that the height is 0.5 meters. The trough is being filled with water at a rate of 0.3 cubic meters per minute. How fast is the water rising? When it's 25 centimeters deep. So take a look over at the picture here. Notice that there are a lot more variables than normal. There is the height, there's base 1, there's base 2, and there's the length. This little h1 that they're talking about the height at a given time. And in this case, they're talking about when it's 25 centimeters deep, which of course would mean 0.25 meters. So just like the previous problems, what we want to ask ourselves is, are any values constant? And in this case, there's actually more than one value that's constant. So if we talk about things being constant, what we've already seen in our previous problem is that the length of the trough from the front to the back, that is going to be constant, which in this case, they tell us is 6 meters long. So I am confident that the length of this trough is 6 meters and it will remain 6 meters. In this case, there's actually a second value that is constant, and that's the length of base 1. So the fact that base 1 is 0.3 meters, think about what's happening as you fill the trough. As you fill the trough at this point right here, the length of the height is different however high you fill it. The length of base 2 is only from the left to the right, whereas if you fill it up to here, notice there's a different height and there's a different base 2. So base 1 actually doesn't change there. So that is a constant as well. So the fact that both of those are constant means that I can actually plug those into my formula. So speaking of formulas, we are talking about the volume of this trough, where the face is a isosceles trapezoid. So remember, it's 1/2 the area of the base. The area of the base of a trapezoid is the height times base 1 plus base 2, and then times the length of the trough. So if I go ahead and plug in the values that I know 1/2 times h, then I know that I can plug in that base 1 is equal to 0.3 plus, don't know base 2, but I do know that the length is 6. If I clean that up just a touch, if I move the 6 to the front, I'm going to get 1/2 h times 6, which is going to be 3h times 0.3 plus base 2. So this is where I currently am in terms of the volume of my trough here. And now I want to go back through and see if there's any other additional information that I should be adding in here. So we are ultimately looking for how fast the water is rising. So if we're looking for how fast the water is rising, we are looking for dHdt. If we know that the trough is being filled at a rate of 0.3 cubic meters per minute, that means that we know dV/dt, and 0.3, and that would be cubic meters per minute. Oh, sorry, cube, not squared. Sorry, I know it's getting a little bit crowded here. I'm going to move on to the next screen in a second. So as I take a look at what I have and as I take a look at the information that's given, I have two variables. I have a height and I have a base 2. If I was to try to take the derivative right now, I would, of course, be in a situation where I would have to know dH dt, which is what I'm looking for, and I would have to know dB2 dt, which is something that I also don't know. I don't know how fast base 2 is changing. So just like in the previous problems, I am going to have to set up a ratio. I'm going to have to set up a ratio between the height and between base 2, which I'm going to go ahead and do on my next slide. So base 2 of this trough compared to the height. They're telling me in this problem that the length of base 2 is 80 centimeters, which remember we made into 0.8 meters, compared to the height, which is equal to 0.5 meters. So I'm going to go ahead and set up that ratio. Because on the right-hand side, they're both 0.8 and 0.5. You can actually multiply both of those by 10 and cancel out the decimal. So B2 over H is equal to 8 over 5. Cross multiply, 5 times base 2 is equal to 8h. Base 2 is equal to 8h over 5. So that's the money step, just like the first two problems. Even though it looks a little bit more complicated, don't be surprised, don't be fooled by the base 2. It's still just a simple substitution. Now that I know that base 2 is equal to 8h over 5, I'm going to go ahead and plug that into what I was left with on the previous screen. So as a reminder, where I left off on the previous screen was the fact that 3h was equal to 0.3 plus base 2. Make sure that that's right. So 3h, times 0.3 plus base 2. So now I'm going to go ahead and make the substitution for base 2. So volume is equal to 3h times 0.3 plus 8h over 5. Then from here, I'm going to go ahead and distribute. So 3h times 0.3, that's 0.9h. 3h times 8h over 5 is going to give me 24h squared over 5. That is actually fantastic because now I'm down to only h's, which means that when I take the derivative, I'm going to get dv dt's and I'm going to get dh's dt, but life is going to be good because I'm going to definitely be able to solve from there. So this is my ultimate volume equation. So now it's time to do the calculus, which means take the derivative. So take the derivative of the left side, you get dv dt. Take the derivative of 0.9h, that's going to be 0.9 times dh dt, plus, so 24 fifths, h squared, bring down the 2. 2 times 24 fifths is 48 fifths. H to the 1 less power, dh dt. So from here, we know that dv dt, we knew that that volume was changing at 0.3 meters. Then we also know that we want to solve this problem at exactly the time when the height is equal to 0.25 meters or 25 centimeters. So 0.3 is equal to 0.9 dH dt plus, so 48 fifths times 0.25 is 2.4 dH dt. Add up all my dH dt's on the right. So 0.9 plus 2.4 is 3.3 dH dt, which means if I divide 0.3 by 3.3, that is how I get dH dt. And if you go ahead and simplify that, then dH dt is going to be equal to 1 over 11, which is equal to 0.09, and the units would be meters per minute. Probably should have changed the color at some point, but oh well. So certainly a lot going on here on these two slides, but I don't think it's anything that you can't handle. Let's just go back to the previous slide for a second and just kind of summarize. So again, in terms of the shapes, try your best to sketch them if you can. Otherwise, You can always just kind of visualize it. When I go to set up my problem here, not only is the length of this trough constant, but the value of base 1 is constant as well, because that's not changing along the bottom. So I went ahead and plugged those values in immediately. I also made sure that I converted everybody to the same family, so meters for everybody. Once I plugged in the values that I knew, I realized that unfortunately I had 2 variables, both height and base 2. That was too many variables for me to solve for. So on the next slide, remember, I then set up a proportion where I could eliminate the base 2 and instead replace it with something in terms of h. Once I did that, a little bit of combining like terms, taking my derivatives, plugging in my values, and ultimately ending up with 1/11 or 0.09 meters per minute. So again, these problems are only getting a little bit harder and a little bit longer, which is why you have exactly 2 of them tonight. I think that they should probably be on the easier side, but even as complicated as some of these problems may have looked, the bottom line is that at some point you have to make a substitution in order to get down to just 2 variables, one on the left side and one on the right. So thanks very much for tuning in, guys, and we will catch you next time.